some values that are kind of weird, and so I'm going to zero that. Okay. And so they should be pretty close to zero. They're not going to be perfect. And again, Christina, if you tilt yours up like this, you see that force plate 1 is changing. So she is force plate 1. Now if you could put yours vertical again. And Gino, if you could move yours. So he is force plate 2. But we want to name this. So if that's force plate 1, what force would it feel? Like if they push against each other, which go ahead and do that now. Force plate 1 has a force of who on who?
Force plate 2 on 1? Or
Okay, but who's doing
Gino
this?
Gino on
Gino on Christina. So the red one, we're going to rename that. Okay? So we're going to call it F Gino on Christina. Okay, and it'll be G on C. Okay, just something like that. So that'll show up like that now. Force plate 2 would be what?
Christina on
Christina on Gino. Okay? Now, if we use the definition that I've started to establish in a bunch of classes, and that math uses for a number line, the left side of our room is negative, and the right side of our room, which is of course erased over here, is toward the positive. Okay, so we tend to think about that way mathematically. We'll think about that way in here in terms of vectors as well. So which one of theirs should have a positive direction of force acting on the force plate? In other words, which force plate would have a force going in that direction?
Gino.
Which one? Force of
Christina.
Gino on Christina is pushing that way. So we're going to make that still read positive. I think what this is going to do then, Christina on Gino, you're pushing that way. We're going to make it negative. So the way that I can do this, I can basically click on the force plate and reverse the direction. So now it's going to read negative. So let's hold them vertically again. And we'll zero them again. And so now when you push, one of them should be getting more negative and one should be getting more positive. So go ahead. So something like that. Okay, that's pretty reasonable. Now I need you to get out of your lazy boys, off the chairs. And so now I would go ahead and start this.
Oh,
Or if it's already started, that's fine.
yeah.
Okay. No worries. I'd rather have more than less because I can edit it out. So essentially, what we want to do now is we're going to have you two push against each other. And I'd like to have you push against each other with approximately the same amount of force. And what I'm going to do is I'm going to click this, and we're going to make this window really big so hopefully we can see all that. Time is big. Of course it didn't do that. I guess it's bigger than it goes. Okay. Never mind then. All right, so holding vertically. And I'm going to ask you both to stand approximately in the same spot. Okay? Ready? Close but not touching yet. Close but not touching. Okay, and start. Push harder. Hard. No, not that hard. Not that hard. Not that hard. No, harder. Push harder. Okay, now, okay, we're good. All right, so I'll auto scale that to make it a little bigger. What do you notice about the force of Gino on Christina compared to the force of Christina on Gino? You can grab your seats again for a moment. What do you notice? Eric? What do you mean by inverted?
So as Gino's goes up, hers is displaying the same exact lines that it's now.
Okay, so I heard, I think, like mirror image or something like that. So how does the force of Christina on Gino under this demonstration compare to the force of Gino on Christina? How do they compare? Sean?
It looks like Gina's pushing it maybe a little bit harder.
Okay. How do you know?
Because the lines go a little bit farther down.
So show me where you're talking about.
On the blue line.
Okay, where on the blue line?
Like in the beginning, like a little bit past 2, like 2.5-ish. It's
Okay.
a little bit
So like
farther.
here?
Yeah, it's a little bit farther than the inverted, where Christina's would be.
I
on
don't
the
see
bottom.
that. Like for me, that distance is about the same as that distance. Within uncertainty. You see another spot where you think that. I mean, just looking.
For a little bit past the 8. It's a little farther.
Okay, this looks like it might be a little different. Okay, now you do have to be a little bit careful because there's some uncertainty, as with all measurements, right? So if you can stand up, push against each other again. We're not going to collect data again, but we're going to do this. So pushing, 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 and depending on how they do that and how they hold that, it may not be perfectly vertical at all times. So that actually can be a little bit uncertain. So within uncertainty, pretty darn similar. But I think that 8 seconds is maybe a couple of newtons off out of 100. For us, that's not too bad. So I want to do another demonstration with this. So can you think of a demonstration we could do where they wouldn't have the force on with Gino and Christina, wouldn't be the same as the force of Christina and Gino? A possible one to try. Ryan.
Gino's standing up and Christina's in the chair.
If they're different height and an angle, that's going to be a problem
Okay.
with how we measure it. So we're going to assume that at least for right now, we're not going to have them in the chairs when they're doing their measurements. We might do that later. Yeah?
Would it make a difference if she was walking backwards and I was walking forwards?
Okay, so you want to push her around then. Okay, so stand up, both of you. Okay. Chairs off to the side. So what we're going to do is we're going to start down here. We're going to stretch your cords out fairly far. Okay, very good. And now hold it perfectly vertical. And I'm going to re-zero. Okay, perfect. Yeah, someone keeps changing. That's not too bad. Okay, and then when I say go, hold on. Ready, and go ahead. Push her around, push her back, push her back, push her back. Oh my goodness. Now, Kristen, hold on, okay. Push her back, keep pushing her back. Okay, so, wow. So what do you notice?
About the same.
So even though you were pushing her that way, right?
Yeah.
We had a change in motion, right?
Yeah.
At any instant in time, and we can look at any instant pretty much by doing these things and like getting pretty close. And again, they're not going to be perfect because we have a little bit of uncertainty with things. They're pretty darn good mirror images, right?
Yeah.
So that doesn't look like you really pushed on her more than she pushed on her. So, Christina, congratulations. According to this, you're just as strong. Which is nice. Can you think of a way where we could show that Christina might be stronger than Gino? Or another demonstration we could do?
You just have them run into each other at the same time.
Okay, we can have them do that. That might be a short time interval of force, but we can do that. Out of the chairs. Out of the chairs. So hold it perfectly vertical. And again, I'm going to zero as best I can. So what we're going to do is we're going to have you run towards each other, touch the plates, keep them vertical, and then whoosh. Whenever you're ready, go ahead. Ooh! Now you're not holding it vertical now, which is a problem. Because anytime this is going, like let's do that again. You gotta hold it vertical the entire 10 seconds.
Come on, Christina.
Ready? This still looks pretty good. Gino, you're not vertical. Whenever you're ready. Oh my goodness, look at that. Oh, it's a battle. Who's pushing harder? Who? Oh my. Oh my goodness. Woo. That was fun. All right, so who's pushing harder?
What is that where they flip?
Okay, that's a little bit weird up here.
Yeah.
Remember, we're pretty close to 0, and I'm not exactly sure what's happening with that. I think, essentially, it's kind of a mirror image. I'm not exactly sure. I've seen inconsistencies in the past. The fact that it both happened before it got really, really big may have something to do with how it's sensing the initial contact. Because right here it's basically saying you both have like a negative force or pull, which I don't think really happened. Unless you were like, almost like bracing or something or pulling back on it, and then the scale could feel a little bit. Well, crap, these are like the most boring demonstrations ever because it seems to show the same pattern. What other demonstrations do you want to do? Test if we can get something different.
I don't think we can.
Why not?
Because
Are you saying they're not good enough?
there's always an equal force back
On what?
on the force being given.
So with an interactive force pair, you're saying that every force has an equal and opposite force pushing back, if it's part of the force pair.
Well, if you want to be that cliche, yeah.
Cliche, wow, that's kind of an insult. Okay.
Yes, sorry.
That's it. Hey, don't worry about it. You're fine. My question is can you think of a demonstration that wouldn't show that? Yeah.
Oh wait, no, never mind. I was gonna say something, but I guess it would show.
Let's see. What do you think?
Well, if you had another person while they were sitting in the chairs push up, like try to do the same amount, see how far each of them would go, but it would still read that, but it would show a different effect.
Yeah, it's hard to say if you have a third person in between, because then we don't know whether or not it would be transmitted through. In other words, but I believe that actually Ben wants to demonstrate this. This is going to be kind of fun. Ben, come on up here. I've never done this before. I like when people give me good ideas. Okay. No, Mr. Forrest. Sometimes I'm confused. Okay. So at this point, what we're going to do is we're going to have Ben stand in between them, and they're both going to push and squish Ben. Now, this is why I say I don't know if this is a great demonstration or not, because in reality, it's Gino pushing on Ben, Ben's chest or whatever pushing back on Gino, and then Christina pushing on Ben, Ben's back pushing on Christina. So we don't know necessarily if those would be identical, but we can give it a shot.
I actually meant for him to push on them, like with equal force with both arms, to have one on Christina, one on Gino. That way he can put an equal force, because you don't know if they're going to exert an equal force.
Okay, so like have his hands out like that?
Yeah, and him pushing.
Okay, I don't care what you make Ben do, it's not me. Okay, so stand up. Okay, so you're going to want to be pretty far apart because he's got a big wingspan. Okay, so Ben, your hands are going to come out. So now stand back even more. Okay, and what I'd say is this: don't touch it yet. I'm going to try to make it again 0. I like this because I've never done this one before. And whenever you're ready, go ahead and push on it. But be aware it's hard for him to push back super strong because of. So we're not, yeah, she's going at an angle a little bit there. So the pattern is definitely not as nice, right? Because we've got some other things going on. So let me try it my way just because I'm curious. Okay, so now you're going to have to flip this way. Okay, vertical again, wait a second. No, not there. It's not like we're doing the automatic external defibrillator. Clear! Which would be kind of funny. Shouldn't be doing negatives that much. Boy, nice and stuff. Okay. Oh, I already did that like 4 times. Okay, go ahead. So the general shape is still okay, but it's definitely not great, right? So I don't think that's reading directly interactive force pairs, but we see probably there's some other things going on. Yeah.
I actually meant for them to sit in the chairs and then that way when he
Okay,
pushes-
perfect. Ben, you can sit down.
Go.
I'm
Okay, so
sorry.
now, that's okay. It's okay. I like it. So we're going to have you sit in the chairs at this point. And we're going to have you play patty cake with these in just a moment. So you probably want to put your feet, you may need to like move that chair up a little bit because your legs are longer right there. Actually, I want you both stand up for just a minute. So similar on here is there's the like, there we go, a little bit. So you're going to definitely want to keep your feet off the floor. So legs kind of back, and then don't push directly yet on each other. And go. Okay, hold yours vertical still. But you don't have to come back and touch them again. That's okay. We'll do it one more time. Nice and vertical. Ready, and push off. Perfect. Now hold them vertical for a while. And I just stopped it there, so that's fine. So that's pretty much the same force, right? So that was actually useful to see because they were directly touching. Any other demonstrations you can think of? So what does this suggest about interactive forces? So how have you heard Newton's third law before?
Every action has an equal and opposite reaction.
So here's why I don't like that. We're going to go out in the hallway and do this demonstration with them again because we can maybe do it in here. It'd be fine. Forces absolutely look equal in magnitude and opposite in direction. And they act on different things. Gino's force was acting on Christina. Christina's force was acting on Gino. That's always true with force pairs. They act on different things. But I don't know if I believe that about the actions-reactions. So if you could put those up here, sort of set them down. I'll turn that off for a minute. So now you're going to face each other. A little bit out from here. And you're going to need to come up a little bit. And Jake, I'm going to need you to be a spotter. You're going to need to stand up. So they're going to push off each other. They're going to play patty cake and just push off with their hands. We know from what we've seen before, they're going to have the same force. We just saw that, right? Okay. So hands up and get ready. Hold on, not yet. And I want you to push off pretty hard on the count of 3. 1, 2, 3. Well, that didn't seem fair. How did that happen? Because they have the same push. Johnny T, what do you think?
The force exerted from Christina to Gino was not enough to change his motion.
Was it less force than he pushed on her?
No, it's the same force, but the force changed Christina's motion, but not Gino.
Why? Why would it change hers and not his? There's a couple people with hands out. You can answer.
Masses.
Gino has
You're
more.
massive. You're not. That's a huge idea in terms of understanding things about forces. So when we look at how motion changes, and both their motions changed, right? They were at rest and they both moved. But the amount of change, the rate at which motion changes, depends on 2 things. One of those things is what? The amount of force. If we have more force, would we have a bigger change of motion or a smaller change of motion? Bigger change of motion. And it's only when we have an unbalanced force, right? So what else affects how much motion would change? Mass. Would more mass cause a bigger change of motion or a smaller change of motion? Smaller change of motion. So that's not horizontal line. I know it's not, but I didn't want to point it out because I thought people would be upset if I drew it a third time. But I'm going to have to do it now. Better-ish. Okay. So I don't like to just call these force and mass, because sometimes there's more than one force acting on an object, right? And sometimes we're not sure what the mass is that we're talking about. So when we look and see the rate of change of motion, which is what acceleration is, it's a ratio of these two things. It's always a ratio. And I would call this a net force, right? Or an unbalanced, the amount of unbalanced force. And I would call that the total mass. And that is Newton's second law. So we just used the third law of interactive forces to come up with the second law. And the reason that I don't like the for every action there's an equal and opposite reaction is they didn't react the same. There was not the same reaction there, because the same force caused a different reaction in her than it caused in him. Forces are the same, the actions and reactions aren't. So this is kind of a big, obviously kind of a big deal. And that's probably okay to stop taping at this point.